Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show. Today, bringing another really awesome guest involved in science and technology, creating a better tomorrow for all of us. Today on the show, we have the honor of being joined by Dr. Brian Grierson, who is a leading physicist and engineer in magnetic fusion energy, is currently the director of fusion energy technologies at General Atomics, located in San Diego. And in his current role, he is responsible for leading the technical vision, the design strategy, and the integration of plasma physics, engineering, diagnostics, the whole tritium fuel cycle set of technologies for various fusion pilot plants aimed ultimately at moving fusion from experimental facilities towards viable large-scale commercial power. Dr. Grierson's career bridges academic research as well as the applied development environment, did his bachelor's at the University of Wisconsin-Madison, majoring at the time in applied mathematics, engineering, and physics, with an emphasis on nuclear engineering and plasma physics. Then he went on to pursue graduate studies at both Columbia University, where he obtained his two masters, actually, and a Ph.D. In applied physics and applied mathematics. After his Ph.D., Dr. Grierson joined the Princeton Plasma Physics Laboratory, there initially working on experimental diagnostics and plasma behavior at the D3D National Fusion Facility, operated by General Atomics, as well as other Tokamak projects. He also held roles including Associate Research Physicist, Staff Physicist, and Research Physicist in PPPL's ITER and Tokamak's department. In 2021, he joined General Atomics to direct their Fusion Pilot Plant Design Hub and served as director of the Fusion Pilot Plant Design Hub for 4 years. Also played major roles in various partnerships, such as General Atomics' collaboration with Savannah River National Lab to ultimately address the issue of tritium fuel handling, a really crucial component of making fusion power practical. A lot of really cool topics that we don't normally get into today, but really honored to have him with us. Dr. Brian Grierson, thank you so much for taking time on the show today.
Thank you very much, Ira. It's a pleasure to be on the podcast today and look forward to the conversation.
Yeah, I'm really looking forward to this one. And again, I dabbled a little bit in fusion on a couple of past episodes, but really looking to get into a lot today with you. Would love to start off, as we typically do, by going back to the very beginning. I make it my responsibility to sort of take a look at your early work and took a look at your Ph.D., which was entitled Interchange Turbulence in a Dipole Confined Plasma, which, among other things, had to do this really interesting something of CTX or collisionless Terrella experiment, which, and I'll let you run with this one, sort of back in the days in the early 60s, was sort of one of the initial sort of plasma confinement concepts at the time that was being developed. Take us back a little bit to sort of what got you interested, not just in plasma physics and infusion, but a little bit about how this topic specifically became your PhD dissertation.
Yeah, sure. I'm happy to go into some of that history. Well, first of all, I got into fusion and plasma physics as an undergrad. I was really inspired by, frankly, very technical challenges. So engineering and scientific challenges, and as we all know, fusion is one of the holy grails of scientific and engineering and understanding, because it has the potential for a new carbon-free energy source. And as the world is increasing in its energy demands, it has that altruistic fusion saves the world kind of element to it, combined with the fact that it's really hard tech. And I knew that going into a field like this, I'd be working with people who are dedicated and also dabbling in all different fields of science, engineering, and mathematics. Fusion combines many of the different disciplines, including fundamental physics. It even has chemistry and material science, nuclear engineering, and mechanical engineering. So that is what really kind of inspired me from the early days as an undergrad. Also, when I was an undergrad, that's when the US rejoined the ITER project. And so at that time in my career, I certainly saw that the rejoining of ITER as a real opportunity and inspiration to get involved in fusion energy. And so as an undergrad, I worked in a couple of laboratories, got my hands dirty, including things like working in machine shops and lathes and building components for fusion devices. And I initially had worked on a device that's more like a cylindrical device. It's called a plasma mirror that uses strong magnetic fields on the ends. Helped construct that facility. And some colleagues right now that I know got their PhDs on that facility. So there's a real lineage there. And then when I went to Columbia, I continued the theme of working on plasma confinement concepts that were slightly off from the main line. The main line being the large tokamaks that are these donut-shaped devices that are one of the most studied and researched types of devices. But I also saw opportunities in investigating other types of plasma concepts. There's a saying we kind of have in the fusion field that, once one concept demonstrates the technical viability of fusion, there will be many others that follow. And in those early days, I was kind of diversifying the concepts in which I was performing research and getting to know and understand. I also really valued the small scale laboratory environment where I had control over the operation of a facility. I could run experiments more or less at the time that me and my local colleagues could execute. There was a bit of I guess not a hesitation, but I preferred that route rather than being a face amongst the crowd in a larger program. But eventually I knew I wanted to join the larger, more mature and more studied concepts. And so at Columbia, I had that opportunity to work on a novel concept, which was a dipole. Actually, it's very interesting. There's a company that was just started recently that is called OpenStar in New Zealand that is pursuing the dipole as a fusion machine for producing net electric power. And so that concept continues to live on. It's very exciting for them. So following my PhD at Columbia, I spent some time physically at Princeton, at the Princeton Plasma Physics Laboratory, but then quickly headed west out to San Diego. And I maintained my Princeton affiliation, but I did my research on the D3D National Fusion Facility, which is here and is still operated by General Atomics on behalf of the U.S. Department of Energy.
Awesome. Yeah, and when you mention, you say mature and studied, and again, looking at, the model, so the collisionless Terrella experiment that you published on, I did a little research there, and that sort of links back to one of the visionaries in the space, a Dr. Winston Bostick, other major names, obviously, that have been sort of looking at the stars and the power of the stars the last 100 years. Lyman Spitzer that ultimately founds what becomes PPL. You have names like Sakharov and Tokamaks, and even for those of many out there that went and saw Oppenheimer, we saw Edwin Teller there. Think about the H-bomb a little bit beforehand. Obviously, we're not talking about atomic weapons here, but nonetheless, that leads to laser fusion. And we did profile, as you know, some of the inertial confinement experiments at Lawrence Livermore. Talk just a little bit, if you would, about the history here, because it is history, again, that goes back a century to people looking at the stars saying, okay, there's the killer app right there. If we can harness that and bring it down and confine it properly and set it off properly, we're going to do some amazing things. But talk a little bit about the history here, because this is,
Sure.
again, as you said, there's a lot of history here, mature things that, we move them a little further and we're going to be in a really interesting place.
Yeah, definitely. So the history is really fascinating. I encourage your listeners to at least get a Wikipedia level understanding of the history of fusion. And it really starts with the fact that if you look up and see the sun or the stars at night, that is the engine, that is the process that drives the universe in terms of producing energy. And so it's been said that the universe down selected on fusion a very long time ago as the ultimate energy source. And so for a lot of time, people have been trying to bring a star into the laboratory and then eventually field it as a commercial product. That's always been the vision. And there's been a number of breakthroughs that have occurred. Very early on, there was a wide range of potential concepts that were explored. And I would say if you point back to the T3 Tokamak that was in Russia, was the first one to demonstrate high plasma temperatures, finally getting to the point where you're at the temperatures that are needed to have the fusion process actually initiate. The unit is called a kiloelectron volt. It's kind of an odd unit, but this is like 100 million degrees centigrade, more or less, if you were to think about it like a temperature. And that confirmation that the Tokamak was able to achieve those fusion relevant temperatures really produced an explosion of domestic research programs in all the countries that had sufficient R&D and infrastructure to pursue fusion as an energy source. So there were tokamaks that were created all over the world, various types of configurations, various versions, some large, some small, different aspect ratios and shapes. Then the next really big event, I would say, was around the time of the oil crisis. And that's when the reliance on foreign sources of oil and the need for new sources of electricity generation and power, that's when major investments were made. There you had machines like the Joint European Torus, it was called JET, which was created at the Cullum campus in the United Kingdom, and the Tokamak Fusion Test Reactor, also known as TFTR, which was constructed at Princeton. And these two facilities were really in a race to make use of the two primary fuel sources that are used for the most mature approaches to fusion, which is combining two isotopes of deuterium and tritium. And so these were the first machines to make use of those fuels at a real scale, approaching the scale that would be needed for a demonstration type of facility. They didn't achieve the ultimate performance that they aspired to, but they made very meaningful achievements in terms of the physics basis. They pushed farther than any previous machines, and they also had the development of the technologies associated with them, things like high power neutral beam injectors, in order to get the temperatures of the plasma up to those fusion grade temperatures, radio frequency and microwave heating and current drive systems, which are the technologies that are needed to be fielded for a fusion power system, like an actual like a commercial system. And they really laid the groundwork for the physics basis for ITER, and provided confidence that ITER, once constructed, would achieve its mission, which is to generate more fusion power output than is input into the machine. And that's pretty much where we are today, is eagerly anticipating the completion of construction and the operation of ITER. That's from the magnetic fusion side. From the inertial fusion side, there's been a parallel development program. The National Ignition Facility right now is the world leading facility for inertial fusion. It goes a different direction than magnetic fusion. Magnetic fusion uses magnetic fields to confine the hot plasma, whereas the inertial confinement fusion uses pressure to compress the fuel. One is really dense, the other one is less dense, and they operate at different physical scales. But this ties back to at least my belief that once fusion is demonstrated as being technically achievable, that there will be multiple approaches that eventually are achievable for technically achieving fusion. The market will eventually determine which one is the most economically viable.
And General Atomics has been involved in sort of various aspects of both of those programs, and we'll get to that in a little bit. But before we go there, I would just love if you could talk a little bit about where you are per San Diego and the D3D setup, because this is a system that run by General Atomics, for the DOE. It's been in operation, I guess, since the late 80s, and many of the scientific contributions in terms of proving some initial confinement concepts and how you shape plasmas and all that stability initially tested there. And could you just talk a little bit about where you are, a little bit about sort of what I mean, I guess someone can't just walk in and turn on the Tokamak and do an experiment, but what's the sort of the general structure there and that surrounding D3D?
Yeah, I can talk about that a little bit. So in parallel to the other deuterium and tritium facilities, there's been multiple other deuterium only or hydrogen-based experiments that really have the advantage of being much more flexible in terms of like manned access and performing upgrades and having closer to a hands-on experience for the participants in the program. And so if I talk about the D3D program, it goes back to early days where the influence of plasma shaping or the shape of the plasma cross-section was something that was being very much explored. And there was a number of debates in the community in terms of what is the ideal shape for making this donut-like device. So you can think of, by shaping, what I'm talking about is, if you think of a conventional toroidal donut, right? How big is the donut outwards compared to the cross section of it, right? Is it large in this direction and small in this direction, or is it small in this direction and large in this direction? Or you can have a short fat donut or a wide thin donut. There also is the shape of the circle of the donut. Should it be square? Should it be perfectly circle? Should it be oval? Should it be like a triangle? These were all a lot of open questions that were being explored in the early days. And the name D3D comes from its lineage, which is that the first D stands for doublet, where the initial shape was more like a double teardrop. And that was called a doublet configuration. Then increasingly larger devices were made with that initial shape until the doublet 3 machine was made, which is the largest version of that. And around the time that facility started operating, they realized that if they turned it from this doublet shape to more like a triangular shape, that they would get more plasma volume, that the performance would be higher, and that it ultimately led to a more controllable and viable confinement configuration. And that it influenced other devices that were being built at that time. It strongly influenced the design basis for ITER. And so that's been the D3D program's secret sauce over the last number of years, which is that it's a machine that has a set of magnetic coils that are highly configurable, that are independently powered. So it allows you to make a wide range of shapes. And that, combined with the fact that it is arguably the most well-diagnosed fusion-grade plasma in the world, means that it can achieve some of the most world-leading scientific insights and validate the physics models and our computer simulations that are used for not only understanding the current generation of machines, but optimizing and extrapolating for the next generation of machines that are going to be more powerful, once again, using deuterium and tritium, and should be able to generate more energy out than in.
But yeah, I mean, again, before now, I appreciate bringing up the fuel cycles again. We'll get to that in a little bit. But now I'd love to focus in on what you were mentioning before, because we have both the work of the National Ignition Facility per inertial confinement fusion, and then the ITER work and magnetic confinement. And again, General Atomics been involved in both of those. And sort of the way I look at it is, at the in terms of the inertial work, it's sort of defined as sort of the micro stuff, and thinking about these capsules or holograms that we previously heard about, and how we define them and how we target them properly with lasers to start this process. The ITER work, more macro stuff. I mean, big, large scale plasma physics, thinking about confinement, thinking about large scale magnet technologies and so forth. talk a little bit about GA's role in both of these, because they're very different, but nonetheless, you got the expertise in both of them, and very important that you have this expertise. But take a little time to talk about GA's role here as well.
Sure, happy to. And this is one of the things that, when I joined General Atomics, my eyes were really opened in terms of the vastness of the capabilities and the depths of the expertise of the scientists and the projects that have been executed here. It's kind of a secret that we need to share a little bit more in terms of the amazing work that's being done here. Like I was mentioning, we've been in the fusion uh, uh, area and doing fusion research since the 1950s. The company was founded on fission and then fusion soon after, and has was the originator of the TRIGA research reactors, which are still being used today. The TRIGA actually stands for Training Research Isotopes General Atomics, and it's these are in university programs. They're being used for creating medical isotopes. So that legacy still lives on. In the magnetic side, in the fusion side rather than the fission side, there are two main divisions in GA that work on these technologies. One of them is the Magnetic Fusion Energy Division, which is the one that I work in, and the other one is the Inertial Fusion Technologies. So I encourage your listeners to go to the General Atomics website, and there's information there if you'd like to see it. So first of all, let's talk a little bit about the big engineering projects. And this is October 1, 2025, at the end of August. Well, we recently had a celebration where we brought together stakeholders in fusion as well as political leadership to celebrate the completion of the magnet that is called the ITER central solenoid.
Okay.
It's an incredibly powerful superconducting magnet that General Atomics fabricated and has now delivered to ITER, and it's an engineering marvel. It's what we call the beating heart of ITER. It's the world's most powerful pulsed magnet. The force that is produced by this magnet is said to be able to, if you could suspend it over an aircraft carrier, it would lift an aircraft carrier out of the water.
Nice.
So that's the incredible power of the magnet that was produced, and gives you a sense of the engineering scale. And it's the thing that will be driving the electric current inside the ITER tokamak. And it's the current that breaks down the gas and turns it into a plasma and produces the twisty magnetic field that confines it and will allow ITER to get to those very high temperatures and achieve its mission of creating more fusion power than the heating power that goes into it. So the completion of that was celebrated at the end of August in 2025. We're also delivering major diagnostic systems for ITER. And these are essential for not only the scientific mission, but also the control of the ITER-grade plasmas. Now, on the inertial side, General Atomics manufactures the targets that are used. There's about the size of a peppercorn. And those are the targets that are used in the National Ignition Facility. The targets are made here, and we have a world-leading team of metrology. So understanding how spherical these targets are, they need to be very spherical. Understanding whether or not there's any point defects or any areas of roughness. And then those are shipped up to Lawrence Livermore National Laboratory, who hosts the National Ignition Facility. And up there, they're filled with tritium, and then they're put into the NIF. And actually, the first fusion gain greater than 1, the Q greater than 1 shots on NIF, use the targets that were made right here in San Diego by General Atomics. It's a little known, but it's really a critical contribution. And NIF was able to achieve these new results largely through improvements in the fabrication of the targets. The lasers have been more or less the same for quite a long time, but it's the improvement in the targets that's allowed them to create these world leading and world firsts.
I like thinking again also the size, the magnitude and sizes here that you're talking about. Again, peppercorns to ultimately
Mhm.
fuel very large areas and aircraft carrier pulling magnets. And so, again, for the audience, and we will definitely put the link to the website so they can further dive into
Yeah,
all of this.
I really encourage your listeners
Yeah.
to look at some of the media
Yeah.
associated with these facilities. If they ever have a chance or an opportunity, if they're in the San Diego area, or if some of the labs host tours. If you're in southern France in Provence,
Yeah.
uh, go and visit the ITER site on the open ITER day. I had the privilege of going there through international collaborations, and it is just an engineering marvel.
Really cool. Really cool. Well, Brian, let's segue now to some of the topics that we haven't gotten into. Obviously, ignition and confinement extremely important, but there's a lot of other sub themes that we've not touched on. I'd love to go into these with you so the audience can get further understanding of where we are and where we're going. And I think, well, actually, these two topics sort of merge together. But one, obviously, it has to do with the fuel cycle, and you've been talking about this. But clearly, while we have a lot of deuterium on the planet, in the
Mhm.
oceans, tritium, not so much. We find it in nuclear reactors. We can go to the moon and get some helium-3 and reverse create it, or whatever. But
Yeah.
tritium is a tough one, so we have to think about how we not just create it, but how we move it around. And then sort of the related topic here, this principle of breeding it inside reactors. And again, I'll shut up because I'm going outside, but you can take some lithium and with the magic of what you're doing, also make tritium inside the reactor and something called breeding blankets.
Mhm.
Not a traditional blanket that I got on my bed over here, but take us into this world, because this is all extremely important, that we have a proper fuel source, enough of it,
Mhm.
but then also that we can make it in a sustainable manner, and that it works within these amazing systems that we're building.
Yeah, sure. So if you go back to the very fundamentals, um, the sun produces fusion because of enormous gravitational forces and the
Mm-hmm.
enormous pressure there that allows the fusing of hydrogen, and then that releases energy. There's a nuclear cross section associated with that. That you're pulling together two charged particles that have the same charge. If anyone's taken a magnet, there's one way that they like to stick together, right, where the
Mm-hmm.
opposites attract. And then if you flip it around the other way and you try to push them together, there's that magnetic force that repels them. So in order to get them to touch, you have to push. There has to be energy that goes into the system in order to get those two like charges to touch. And so the sun does that with incredible gravitational force. But in order to do that on Earth, you normally need to get uh, the gas ionized into a plasma, and then you get it really hot and dense enough such that the probability of two positive charges hitting each other and fusing, overcoming that nuclear force, is high enough that you can produce, energy coming out of it, right? Kind of the E equals mc squared, that there's a slightly less mass with the result, and then that produces energy. Um, so in order to do fusion here on Earth, we prefer to use a different set of isotopes of hydrogen. So rather than just hydrogen gas, it would be deuterium and tritium. And so these are two different isotopes of hydrogen. And so why do we do that? We do that because the temperature at which fusion occurs for deuterium and tritium is significantly lower than the other potential reactions. Uh, and so it's quote unquote easier. It's not easy, but it's the easiest one. And it's the one that has been pursued and studied and is the most technically mature at this point, I would argue. Um, and so where do you get deuterium and tritium? Deuterium is naturally occurs in seawater, and it can be extracted. You can buy it from most gas vendors. You can just purchase a bottle of deuterium. But tritium, less so. Tritium is a radioactive material. It decays with a half-life of about 14 years. And so it needs to be produced. And the primary place in which it's being produced is like up in Canada, the CANDU reactors, which are called a heavy water reactor.
Yeah.
And it can be, with the appropriate license, it can be purchased and used for experiments, testing, and stuff like that. So in order for fusion to be a viable energy source, you wouldn't want to just buy tritium. First of all, the world supply of it is not huge, and there's not a lot of like active production of it right now for civilian uses or for commercial applications. So one of the benefits of fusion is that once you get it working and it's efficient enough, you can put lithium around the machine and you can breed your own tritium. So deuterium is not a supply chain issue, but tritium is. And this is what we call closing the fuel cycle.
Okay.
So you have your fusion plasma. What it does is it produces energy, more or less in the form of high energy helium and then a neutron. A neutron escapes and it gets absorbed by this, what we call a blanket, which is like a thick, like probably like a meter scale, thick structure surrounding the donut, like wrapping around it. And that would contain lithium, either in a molten form or in like a solid ceramic. And that neutron then hits that material and it has lithium in it. And then lithium splits. And when lithium splits, it produces tritium. And so then you have to recover that tritium out of that lithium material, either through a sweep gas, if you have a solid structure, or if it's a liquid, you just cycle the liquid through the system with pumps. You can buy pumps for these types of systems. And so that is the circulation of the tritium that becomes extracted and then would be put back into the machine via gas or cryogenic pellets.
Mm.
And that's what we call closing the fuel cycle. Now, if you are following along with your pencil and paper and we're doing your math, you'd say, well, hold on, you only produced one tritium atom for every neutron that was produced in your fusion reaction. And so how can you get more tritium? How can you produce enough tritium to, say, start your next facility? Well, there you have to use what are called neutron multipliers. And there are materials like beryllium and lead that would be sandwiched in or mixed in inside that blanket that when a neutron hits it, you would get two neutrons, and those two neutrons would then produce two tritium atoms. And so now you have multiplication, not only of the energy that comes out, but also the breeding of tritium. And so that's like the fundamental closure of the fusion system that allows it to then be like replicated.
Got it.
And it's then that does not tie it to the initial source of the tritium that you bought.
Right.
So now you have an energy producing system that can be replicated in different physical locations. That is not directly tied to like pulling oil or gas out of the ground in that one location, which is how fossil fuels and a lot of conventional energy sources extract these things out of the earth. It's tied to a technology rather than like an ore or a natural reserve. And so that there's a lot of discussions about how that eases geopolitical tensions and gives energy independence to the country that first develops this technology and makes it economically viable. So that's part of that Holy Grail type of narrative.
And speaking about Holy Grail parts of the narrative, and again, in closing the fuel cycle, ultimately, it gets us. We want the plasma burn to happen, but we want it to ultimately become what's known as a sustainable burn that yields a long-term burning plasma. And I'm speaking out of turn here. But one other thing I wanted to ask about, because just I'm interested in, and I'm sure the audience is as well. A couple of other aspects of again, keeping beyond the aircraft carrying magnet power, there's other components that make sure that this all happens in a safe, controlled way and doesn't go places that we don't want it to go. And again, things that have come up include sort of edge plasmas, which are, I guess, some plasma zone between the actual plasma and the wall of the
Hmm.
tokamak that help manage the different fluxes along the way. And then, as you were talking about before, beryllium, again, other let's say materials or extreme materials that are important that like tungsten and boron carbide. So
Yeah.
about boron in the Chernobyl documentary. But what is what's the future of the tokamak wall in sort of what's the future of sort of the extreme materials that ultimately go to containing this sustainable burning plasma in the long run?
Yeah, I'm happy to talk about that a little bit. Have had the privilege of working with some of the leading scientists and engineers in the US that are in the material science area that know very well some of the challenges that fusion producing machines will encounter once they begin to achieve the levels of performance in terms of the fusion yield, the energy yield, and the neutron flux influence that we aim to achieve in order to, like I said, produce enough heat and breed enough tritium that a fusion system becomes technically viable and then eventually economically viable. The biggest challenge is right now is that you have a lot of systems that all need to come together and work in an integrated fashion
Mm-hmm.
where a number of them are at what we call a fairly low technology readiness level, or TRL. And the challenge there is that the trade-off space, or the trade space in terms of technology solutions and the ones that work together or that will struggle to be compatible is still pretty wide.
Mm-hmm.
Um, on the upside, it means that there's a lot of potential solutions out there that we're not, uh, we haven't painted ourselves into a corner in terms of viable technology options. But the challenge is there's a lot of technology development that still needs to occur to ensure that these systems will function in
Mm-hmm.
the relevant fusion environment. And you had said before, yeah, you need this burning plasma, but then there's also these, materials and the edge plasma and plasma solutions that are needed. This is really a big and initiative, not an or,
Mm-hmm.
because they're so closely linked. Um, by improving the operation of the plasma core, by increasing the confinement and the minimizing the leaking of heating out into the material surfaces, you make the material challenge easier. So these are two things that can be very synergistic. Similarly, if you have a poor confinement solution, your materials challenge is much harder. And so, in terms of the materials, the things that we need to develop and we need to understand is how will these materials change when they are exposed to long operational periods of these fusion devices. The fusion devices produce heat fluxes that exceed spacecraft reentry. Right? So
Mm-hmm.
if you've seen the shuttle or the SpaceX rockets as they come in, they're glowing red, orange, white hot. Fusion produces conditions of heat fluxes that exceed that. And so that's when you start to use materials like tungsten that have very high melting points, right?
Mm.
Tungsten is generally, you see that inside of like light bulbs, right? Those are like the
Correct.
filaments that glow that very, very hot. That's one solution, but it does have challenges, which is that after long exposure in a fusion environment, it can become brittle. It can potentially lose its uh, its thermal conductivity, or its ability to pass heat from the surface into a coolant pipe, and that can cause stresses and potential cracking. And so those things all need to be tested in laboratory devices where you can cycle them in terms of multiple heat cycles, and then look at them under microscopy to make sure they'll survive. The other area is in terms of the breeding blankets.
Mm-hmm.
There's never been a successful deployment of a breeding blanket on any device yet. And the primary reason is that, well, frankly, we haven't had to, but we will need to soon. And there's a lot of different potential approaches. Some of them are likely to pan out in the near term. Some of them are more advanced and will take more development, but may eventually be more efficient.
Mm.
The other areas, and these are areas that we focus on a lot in my department, in addition to the materials and the blanket and the fuel cycle, is the diagnostic systems
Okay.
that will be required to observe and inform control systems
Mm.
to ensure that the plasma is operating in a robust way, that it doesn't migrate into an off-normal state that may cause the facility to have a period of downtime where it stops producing heat and stops producing electricity. The other area is the systems that keep the plasma hot, the heating and current drive systems. So my department works in this area as well. We fabricate and deliver high power microwave transmission lines, neutral beam systems and components for fusion devices. And one of the challenges, frankly, is that every fusion device, because there's many different types, they're all different. The interface requirements to them are all different. Generally, any system, any diagnostic system, heating and current drive system, cryogenic system needs to be custom tailored to that specific confinement concept, whether it's a magnetic, a magneto-inertial, or inertial fusion concept. They're all pretty unique. And
Mhm.
this causes issues with interfaces, lack of standards, and it becomes difficult to have an off-the-shelf item that, for example, I can just sell you in a catalog, and you can plug it into your fusion device, and it'll work because they're all different. So
Mhm.
we're hoping that the emergence of standards and advancement of the regulatory framework for fusion energy systems will incentivize standardization, and that will help uh, machines be designed and built and get that data faster.
Mhm. Mhm. No, it's again, it's amazing all the different angles here, but clearly you're thinking about each one and bringing it all together, which is amazing. And again, for everyone listening, we are ultimately in comparison, if we think about a gigawatt or something of potential of energy, we're talking about fusion needing something only about a kilogram of potential fuel, but
Mhm.
compared to tens of tons of fission nuclear material and literally millions of tons of biomass if we're talking about fossil fuels or other energy sources. That being said, and then just one other thing on the list I wanted to ask about, and I know this is a little further down the line, but when it comes to generating electricity and dealing with, okay, we have everything perfect, and now we got, again, extremely concentrated hot forms of energy that we want to do direct thermal conversion to or other interesting conversion concepts. What are some of the things that you sit around thinking about on those fronts? Again, as you were just pointing out, when you're dealing with this space shuttle hot
Yeah.
entry type of stuff. Okay, very powerful. A lot of where is it going ultimately? What are we doing with it, and what are some of these concepts that you think about on that front?
Well, there's a couple of interesting concepts that have recently been discovered or gotten a new look. And one of the interesting concepts that was recently demonstrated by the D3D National Fusion Facility is that contrary to conventional wisdom, which was making the plasma shape like a specific form of a triangle,
Okay.
which in the community we call positive triangularity, uh, they were able to reconfigure the inside of the machine. They removed some of the tiles, and because it has this flexible control system, they decided to flip that triangular shape to to have the triangle pointed now inwards rather than outwards, which flies in the face of a lot of conventional theoretical analysis. But some earlier calculations and some novel experiments that were done at a facility called TCV in Europe indicated that this configuration may solve some of the problems that a conventional triangularity machine would encounter. And so there were these recent experiments were done on D3D and showed that indeed that you can run the plasma configuration in this reverse triangularity scenario and achieve similar levels of fusion performance in terms of its confinement, but really alleviate one of the challenges associated with that high heat flux that you were just talking about. And it does this by moving what we call is called the strike point in Tokamak lingo, but moving that strike point from being on a small ring to like a larger ring. So it spread out the heat over a much larger area and a larger surface area. And this really has the potential to alleviate the challenges on the materials like I was describing before. And this has all just been in the last couple of years. You mentioned that the D3D program has been around for a while, but like I said, its flexibility allows it to uncover new and novel configurations with a little bit of ingenuity and a little bit of motivation, and to do it fairly quickly, to explore some of these things that are potential game changers for fusion that were frankly pretty unexpected by myself and others. But it just shows once again that there's a lot of scientific research, there's a lot of opportunities for innovation in this space. And so, like I was saying before, it's a real and issue to continue the plasma physics and the fusion plasma science research while we're advancing those engineering solutions, because there are brick walls that you end up going up against, and you need to be able to get yourself out of being painted into a corner. And so things like these types of innovations are really informing and getting people to rethink things that they thought they knew.
And to avoid some of those brick walls, you, like many other industries that we profile on the show, clearly AI having a major role. You had this interesting paper. This was in Contributions to Plasma Physics in 2023 on this deep learning model on plasma control systems. The next year, in 2024, you presented on digital twin frameworks, and again, clearly AI, digital twins, and it's their ilk, very important without having to go over there and turn the Tokamak on and play around and run into a brick wall. Talk a little bit about how some of these innovations and these tools are helping you, obviously, work through these problems before you spend a lot of energy on them.
Okay, yeah, I can talk a little bit about that. It's obviously a very every moment right now there's a new story on AI and the advancements that are happening with algorithms, and a lot of that is based on deep learning and reinforcement learning, and we see it a lot in what are now the large language models that is generally being interacted with by people all over the world. But the same approaches, the same techniques and tools are also used in the hard physical sciences. And the opportunity that we have seen in the use of these tools is breaking a typical trade-off curve. So when we talk about computing and modeling and plasma simulations, there's generally been historically a trade-off curve. And the trade-off is on accuracy versus speed. And that is things that are really fast are generally poor accuracy or very limited domain of applicability. At the simplest level, it's a function evaluation on a calculator. It's a number, it's a scalar, and it's only applicable inside one domain. On the other extreme is running simulations that occupy an entire national supercomputing cluster for weeks. Those are incredibly accurate, but they are heroic, and you generally only get one or two of them to be able to be done. They reveal deep insights, but they are also very expensive. We use the term expensive in terms of the number of computations that are done. And so what the machine learning tools and AI-informed physics-based models are able to do is they break the speed accuracy trade-off. And so now you're able to have models that operate in a multidimensional space that can be used in optimization algorithms that are both fast and accurate. That's been a huge breakthrough. It's very rare in physical sciences to see an innovation that gives you multiple orders of magnitude of capability enhancement without sacrificing something else. And these tools are able to do that. I'm talking tens, hundreds, thousands, tens of thousands of times faster. So now I can do a calculation on my laptop in a fraction of a second that would have taken a week on a national supercomputer. That power is now being unleashed in terms of a complex integrated system optimization framework. At GA, we developed a tool that we think is best in class in terms of integrated modeling. It's called the Fusion Synthesis Engine, or the Fuse Integrated Modeling Framework. And we've been able to show that multi-objective optimization and integrated modeling can come up with new and novel solutions that really, really can take the human out of the loop for a lot of the tedious work.
Mm.
We're expanding them into engineering models. So now these physics-based optimizations can create CAD, or computer-aided design,
Sure.
like physical structures for us to do thermomechanical modeling, neutronics, and all the other heavier workhorse engineering type analyses needed to go to that next level. But we don't have to wait weeks and months to come up with an initial concept. We can come up with an initial concept very quickly and then go find where are the pitfalls, or where are the engineering challenges. And so it's all great. It's all in silico, we say, it's all done in the computer. But its value is only really realized when you have a physical asset by which to compare it to.
Okay.
Otherwise, you're just not confident that everything is correct. You need to have testing. You need to have a completely worked example, and to show where is the domain of validity.
Mm-hmm.
And so that's where facilities like D3D and like NIF were able to validate these tools and show that yes, we've actually broken the speed accuracy trade-off curve, and we now have a new tool that we can then deploy and use in studies for next generation machines. And so it's been really groundbreaking. And I think that what we're going to see that type of efficiency now move also into some of our engineering models, as we will have things that can perform that next level where you really need a subject matter expert and a person in the loop in terms of driving design iterations. You're going to now start to see that being driven perhaps by a well-trained AI agent or something like that can interface with those tools kind of like on your behalf as part of your team.
Really cool. Amazing, amazing coming few years, I gotta say, and it's nice to see tools like that. Although I understand very little about AI, but realize that it's permeating every sort of area and
Sure
theme that we
seems to
get
be.
into on the show. So I'm glad it's helping you out again to figure out and advance things faster. So, but one other thing I want to ask you about before we wrap up, looking out a bit clearly, I mean, we've talked about pretty much every aspect of the process here and where we're going. But again, I'll see news reports come across my desk of little startups and private initiatives that are getting involved in the game. Obviously, General Atomics is the big hit on the block. But I mean, I come out of the pharmaceutical industry, and if we were developing certain medicines, we don't have something we want. We find a small biotech company over here, and we invest in them or acquire them. Is there stuff out there that you obviously leading this set of initiatives at General Atomics? Are there other technologies that we haven't gotten into that you might want to mention, or things that excite you that are sort of a little over the horizon, maybe not ready for prime time at the D3D, but you got your eye on, and you might want to start placing some bets on some of these ancillary tools? What's sort of the environment outside General Atomics that interests you, that may play an important role in where this is all going?
Yeah, there's a number of areas that I would describe as being kind of one adjacency
Mm-hmm.
from core fusion technologies.
Yeah.
And these can be in advanced scientific instrumentation for other applications. There are some organizations are using fusion systems for imaging or
Mm-hmm.
medical isotope production.
Got it.
Some of these systems can be used in telecommunications. So when we talk about power transmission, including
Hmm.
high energy power transmission, telecommunication systems, as well as space communication systems. So there's a lot of these technologies that have like one adjacency away that have applications. Magnets obviously is one that has applications in nuclear magnetic resonance, perhaps,
Sure.
MRIs, right, is a mature technology, but some of those could be made more efficient with the type of magnet technologies that are being developed in fusion. Accelerator systems, so accelerator systems that are used in the high energy physics field are benefiting greatly from fusion developments. And I think that a lot of these one adjacent type of pursuits or markets
Hmm.
aren't just nice to haves. They're really kind of needed.
Mm.
They're needed because it allows those who are developing the technologies to have other streams of revenue and applicability, and adds value and shows that the investments in fusion systems is not just to bring fusion power to the grid, but
Right.
has a broad use base. And I think we need to get that message out a little bit more because as these technologies mature, as the additional uses for them are identified and explored, then
Hmm.
we'll see the broader impact of the investment that has been made in fusion over the last number of years in terms of really high return on investment and benefiting, humanity more broadly.
Hmm.
So that's I think that's where a lot of the inspiration is for those in the technology field. Not only the commitment to developing systems that are needed for viable and eventually commercial fusion energy, but also the broader benefit that technology advancement can have. So that keeps a lot of, at least the people that I work with, that keeps them really motivated. They're very self-motivated for these reasons.
Yeah, it's really, and especially I do a lot, as you know, in the healthcare side, we've been looking a lot of the medical isotopes and then some of the more targeted cancer therapies lately, which are beginning to incorporate this, not to mention obviously all the space stuff and even destruction of nuclear material
Yeah.
using these technologies. So yeah, all really fascinating and very relevant to where we are. Um, Brian, while we have you, what else is coming up? I noticed that let's see, in a few months there's going to be the American Nuclear Society meeting. You're going to be leading a session on the future of fusion energy.
Mhm.
I noticed that you get back to your alma mater, Columbia, and give some colloquia there.
Yeah.
What else is happening? Where else are you going to be besides San Diego in terms of conferences, talks, other initiatives that are public facing that you may want to mention while we have you today? Anything that I missed also, as
Yeah,
probably want
sure.
to talk about.
Over the last year or so, the U.S. fusion community has held a number of meetings and workshops in terms of kind of coming together and establishing a national vision and a roadmap for fusion development. And the U.S. Department of Energy's Office of Fusion Energy Sciences is at least scheduled or planning on having a release of that initiative sometime, I think, next month. I think that's now publicly known. That's been posted and circulated within the community. So
Mm,
that'll be an important moment because then we'll get to see the result of a lot of effort and a lot of backroom discussions and some heated debates in terms of the direction that the field should be going. And we'll get to see that vision and that roadmap laid out, and we can start implementing on some of these new programs and new projects. I think that'll be a important upcoming next step. If you look out further into the future, it's exciting to see a lot of these companies, some of them startup companies, they're doing technologies and now actually starting to assemble some experimental devices.
mhm,
And some of them are pretty unique. And so we'll get to see how well some of these new devices and new concepts are performing.
mhm,
And we're likely to see that in the open scientific literature, things being vetted with peer review, which is still a hallmark of our community. So yeah, probably that's in the next couple of years. I think we're going to see the degree of success. And we're all hoping that there's a very high degree of success and we can continue to build this momentum.
I I look forward to continuing following the momentum, following your work because it's amazing what you've done in such a short period of time. But it's just a really impressive story. Again, we will put all the relevant links in the show notes and the bio. But for everyone again that's going to be listening to this episode across the various podcast networks or who will be watching on the YouTube channel. Again, you've been listening to Dr. Brian Grierson, Director of Fusion Energy Technologies, General Atomics, doing really amazing things, as they say, to realize the promise of fusion and ultimately bring the power of the stars to our planet. Brian, again, I really want to thank you for taking the time to walk through some very difficult concepts with us and explain them with such clarity. Thank you for everything you do there at GEA. And as we like to say on our show, thanks for helping develop and advance science and technologies that ultimately improve the world for all of us. Really an awesome story, and I look forward to continue to follow everything you do.
Excellent. Thanks, Ira. It was a pleasure.
Really great having you.